Well, thanks for making it to the bitter end. I hope some of you are probably here because you're stuck, but thank you regardless. And I'm Kyle. This is Miklos. And we have tips and tricks about keeping Spark on track, particularly things that we've seen about productionizing Spark in ETL. So again, I'm Kyle Pistor. I'm an SA, a solutions architect at Databricks, so handle all things technical across our customer board. I have experience with about hundreds of customers, been at Databricks for about 2 years, and I particularly like to focus on ETL and big data warehousing using Apache Spark. My background, I have a BS and an MS in electrical engineering.
And I'm also a solutions architect. I previously was a systems engineer, which is kind of the same thing at Cloudera. So I have pretty good knowledge of the big data ecosystem, played with all the various tools, plugged all of them together, made them work. It was a lot of fun. And now I focus primarily on Spark and running it in the cloud and understanding the architectures there.
So how we're going to run this. So first is why ETL. Sometimes people new to Spark won't do much ETL on their data, just query it on read. Then we'll talk a little bit about schemas. We've heard a lot about data frames during this whole summit, moving more and more from unstructured to data frames. So we'll talk about applying schemas. Then about metadata, particularly about file system metadata and how to handle that in best practices. And then finally, Miklos will wrap up with performance tips and tricks, as well as how to handle common errors. So ETL, why ETL? So the goal of ETL is to transform raw files that come in, delimited CSV, JSON data, into a more efficient binary format that Spark can handle and read quickly. One of the main benefits to do this is performance improvements, right? Converting from something like JSON or CSV into Parquet is performance. Usually we'll see somewhere in between a 2 to 5x speed improvement just by doing this single process. Tight bindings with Spark, summary statistics that are encoded in the files, as well as the columnar format, if you're only querying specific columns, as well as some of the metadata overhead as well of getting optimal partitions and block sizes. Another benefit is storage savings, right? Whether you're HDFS or S3 or somewhere else, you're going to compact and have smaller amount of data that you're going to have to persist. And this will also help in network I/O. You'll have less data that actually have to transfer. And then there's, of course, always standard APIs to read and write back to the sources if you need to. Parquet is very common across many different systems. You can read it directly in from R, Python, Hadoop, Presto, Spark. So Parquet is common, but if you need to write it back into another more traditional format, you can. And then lastly, more robust queries. You're catching a lot of the errors, providing the schema, clean it up, so when users downstream actually query this data, you've caught a lot of those common things or malformed rows in your data before they actually get to it. So the first thing, common thing when I first get a new set of data, CSV, JSON, is schema. So let's talk about schemas. So, commonly raw data formats, might be log files, commonly delimited data like JSON, tab delimited, or JSON as well. So obviously we're instrumenting everything. Event logs are very common, and those data volumes are just getting huge. So there's a couple of options. Spark makes it very easy to infer the schema directly. So it'll actually scan the data set, infer. So it's easy and quick. And then it's a little bit more work to specify the schema, but it's going to be faster and more robust. And I'll show you an approach here in an example that will actually integrate both ways to make your lives easier when you're writing your Spark ETL pipelines. So let's take, we'll do JSON. It's a little more common in larger data. We'll take a JSON data set and look at the first record in a particular data set. So at the top level, we have a number of fields: time, host, event type, and we have a nested field event, which contains message and info. So if we wanted to read just this one file, it'd be very straightforward: Spark read JSON record number 1. And Spark could scan this individual file. If I did .schema, I would get this fairly straightforward schema of the data with a struct type for the event, which is going to be fixed length with message and type. If we look at the second record, which is going to have more information, maybe a different event type, or maybe there's just more information in this particular event, and we have, you can see we have more information in that nested field: IP, browser, OS, country. And how do we want to handle this? So we could do the same way, read JSON, record star, and what we'd do is we would get the highest combination of that event type as a struct field. So every field would have nulls for those values that weren't there. So IP, browser, OS, country would have nulls for that event. And so you'd have to scan the entire data set to get the possible combination of all your JSON records to build that schema. So that scan's expensive. You also have a bunch of columns that you may not use. So what I'm proposing as a better solution is something I like refer to as the generic specified schema. So we're going to use the inferred schema, and usually I'll take like a sample of the data with the sample, or look at a single partition, and use the print schema command to massage that schema to get it into more format. So originally, it had this struct type where I have the event of type, IP, browser, OS, and country. And what I'm going to do is convert that to a map type. So a struct type has a fixed length of fields automatically, and a map type is able to support variable lengths. In this case, it's all strings, so I did a string type. So the key of that nested field is going to be string as well as the value. And then when I actually do the read, I'm going to pass that custom schema into the JSON record and continue to read. So what is this going to allow me to do? First, it's going to reply, I don't have to scan. Anytime you specify a schema, you no longer have to scan the full data set or some sample to read it. So it's going to be much faster and scalable as you scale up from more than just 2 records to terabytes worth of data. And it's going to be more flexible. You're going to be able to handle evolving or variable length fields as you instrument more things, right? Instrument everything. You're going to be able to handle more flexibility, and then it's going to be more robust. Handle some type errors, handle some of those errors initially when reading it. And the nice thing is you can always query those nested fields easily and make views or subtables downstream once you've done this initial ETL step. The second thing is metadata. File system overhead of listing metadata specifically on the file system is a lot of work, and things are getting a lot easier in Spark as time goes on. But there's a common thing I see across customers who are new to Spark specifically. Commonly, our customers are on AWS, and they use Kinesis Firehose. And Kinesis Firehose partitions raw data by arrival time. Usually there's some path of your data, year, month, day, hour. And the data is like as it trickles in from the upstream producers. So it's going to have many small files that are going to be kilobytes or tens of megabytes in size, which are not optimal, as well as often too little data per partition. You could have the opposite extreme. Have a lot of events happening where you have too many files per partition. But most people aren't producing very much data per individual hour. So the naive approach to handle this or do like a large backfill, if you wanted to backfill like a full year's worth of data, is to use only wildcards. So I could do, if we're using that same similar JSON data example that we were doing earlier, if I wanted to backfill all of 2016, I could use wildcards all throughout, do some ETL, and then choose to partition it by that same date and write it as Parquet. Why this is a poor approach is because my data is technically already partitioned as it arrives. But Spark is not aware of these existing partitions, and you're going to have to force in a very expensive shuffle. So if your data is relatively small, this may not be too challenging, but if your data is scaling to hundreds of gigs, terabytes, this is going to be extremely expensive if you want to convert formats for a large time frame. So a more scalable approach is to actually create a list of these paths that you want to backfill or process. And I usually do this with file system ls commands to do that backfill, either on S3, dbutils if you use Databricks, or some HDFS commands, and build a list, and then iterate over that list to backfill, preserving those partitions we already had. So I create just a very simple function in this case, read that data with the individual path, and then maybe do some more ETL, and then do a coalesce if I want to reduce the number of partitions, which I'll talk about in a minute, and then write it back to my path, and do a for each over each of these. So this is nice, but in my case, individual hours in that example, this would take forever, right? I have 24 hours times 365. This would take forever. So what we can do is we can parallelize this. We can parallelize it with multiple threads in Scala.par or with Python multi-threading. Instead of the for each, I'll do a par for each. And you can specify your thread pool and do 8, 16, whatever number of partitions you need to meet either your SLA or saturate the cluster that you're working with to backfill as fast as possible. A couple of other sync path considerations of where you're writing your data. Commonly, specify the date instead of each year, month, day as an individual partition. So instead of doing it this way, year, month, day, it's hard to do ranges. There's also people who are actually writing their own queries. There's a lot of predicates, to enforce predicate pushdown that they would need to write. So instead, have a date similar or something like this, and you can specify date ranges must easily, and there's only one predicate to include in your query, making it easier for end users, data scientists, SQL users to query this data. Second, block sizes. So Parquet is actually splittable. So larger is okay. So don't be afraid to have larger block sizes with Parquet, the actual files written to S3 or HDFS. But if you have too large of a block size, only a single thread can write this. So if you have 2 gigs, it's going to take much longer than a 500 megabyte file. So I usually shoot for somewhere around a gigabyte of block sizes of the data actually stored on the file system. And, and then up to you on that. And then lastly, again, this is probably redundant for many of you, but blocks or gigabytes per individual partitioning. The first time people try partitioning, they usually tend to go to one extreme or the other. Some people don't do any partitioning at all, or some people over-partition, thinking it'll speed up all their queries. But each one of those partitions in individual files has an overhead of having to list that and store that on the driver. So usually I shoot for the tens of gigabytes, somewhere between 30 gigabytes per partition tends to be optimal.
Cool. So now I'll talk about some performance tips and tricks that I typically do. So performance optimizations. So Spark comes with the Catalyst optimizer, and I think a lot of people have heard of this. It helps speed up your queries and your plans. But ETL is the first phase of getting some of that speed improvement. And one important thing that I like to point out is that null values need to be interpreted appropriately. And so null values could come in from various systems in different formats. Maybe you have an empty string and that represents null values for you. Spark doesn't know that, and you have to tell Spark, how do you interpret the null value? Some other systems like Apache Scoop, when they scoop data in from various SQL sources, they have special quoting structures to represent null values, and that's what I've shown here, this //n. And so there's options within Spark to help translate some of this data. And this one is reading a CSV file, and we're finding these special characters or empty strings to translate it to null values. Now, with null types, there's performance improvements that we can actually do for you so that you're not specifying some of these out yourself. And for this particular example, what I'm going to go through is a few examples of 2 queries where I'm doing a join. And maybe your join keys could have null values. And here you can see on the left-hand side, we have some null values that are just empty strings. And then on the right-hand side, the actual null replacements when using that API that I showed earlier. Now, how do you compare the performance and look at what's going on underneath the covers within Spark? And that's where I jump into the Spark UI. And within the Spark UI, there's a SQL tab at the very top. And this will show you the queries that you're running. It will generate the query plans, and you can see what's going on underneath the covers. Right? Here you can see these 2 stages, which is the stages for the joins, the left and right hand side of the join. You can see whole stage code generation, which is code that we've generated on your behalf to try to improve the speed of the query. And you see these filter operations, where we try to filter out any null values. And here, in this example, we're using that empty string test data set, where you can see there's 50,000 records, and there was 50,000 records after the filter. Not very helpful. And so you can see that we're attempting to improve the job, and it took about 13 seconds, but we didn't get much improvement. Now, if we were to use the actual null values that we've ETL'd, you can see that the runtime changes pretty drastically for this small data set. Goes from 13 seconds to 3 seconds to complete. You can see the actual filter output go from 50,000 to about 26,000. So my data was quite sparse in the type of keys that I was using when I'm doing the join. I actually helped improve my performance because it was able to filter out these values. Now you could filter out the values manually. In your join, you can add a where clause where this key is not null, and you would get something similar. Or you can let Spark handle it for you just by making sure your data types are in the proper formats. Another thing that it's common issue that we see when people start to use the data frames APIs and trying to use them to join various records together is using the join API with common key names in the two tables you're attempting to join. So say you have an ID column in one table and an ID column in the other table. You write out this join, and if you print the schema, you're going to see these two ID fields in the output. Now, if you try to reference or select one of these ID fields, it's going to throw an error saying ambiguous ID column. I don't know which column ID you want, right? And they're the same value, so you actually don't need them. And since Spark actually provides an API to just keep one of those columns in the output. And so you don't need to try to drop the duplicate column here or try to massage and alias it to a different name before the join. You can actually just use the .join and provide that single column name, and we'll actually have an output with just that single ID, right? And so a lot of these are documented within the data frames documentation, and these are really good tips and tricks to kind of save you time and make sure your applications are easier to read and easier to work with. And if you want to learn more about optimizing your joins in Spark, there was a great talk yesterday by one of my colleagues, optimizing SQL joins within Spark. And I think within a week or two, you can go online and look at the videos and the slides of that talk further. So next, error handling. I think error handling is quite difficult on these distributed systems. You don't know where the error is occurring. How do you interpret the stack traces? Sometimes they can be quite noisy. And so what I'll try to go through are a few examples of error handling. One of them is within your data sets, you might have corrupt records, right? Maybe your JSON records are malformed on a few of them, and within Spark, if you're using the JSON reader within Spark, there's actually a column called _corrupt_records. And so if you do have corrupt records, you're going to see those fields here. And you can see that I do have some good data. The top 3 values and the last value are parsed perfectly. And so you can separate your good data and your bad data and potentially improve or fix your bad data, or maybe keep those columns that are valid and null out the rest of the fields. It's really up to you if you can fix those records, and you can separate them quite easily. You can say, give me all the corrupt record values where they are not null, and generate one data set and work with that later on, and then push the rest of them to your production database or whatever data store you're trying to push to. The other thing are handling UDFs when you run into an issue trying to write a UDF. So Spark might not have all the functionality that you need within the built-in functions. You might want to augment that with some other native Python libraries or Scala libraries that you want to write. And so UDFs are really great in augmenting your processing power. And what I wanted to go through is, how do you determine where the error is? And so typically you have this big stack trace. You try to interpret what's going on. This one tells you, the first line doesn't tell you much. It says some error really occurred. If you read through these lines, you can see that it actually failed 4 times, which means it failed once, and Spark has a retry policy of 4. So it'll try up to 4 more times before it actually fails your job. And so this one actually tried to run 4 times. And lastly, you can see at the bottom in the red that one of the UDFs, when I was trying to modify the date time object or the date timestamp, I was trying to add an offset to it, I imported the wrong module when I was modifying my code. And so this helps me understand where the error occurs, and I can drill into my own code and fix that. And so you have to scan down through the stack trace. It's typically in the middle, and it's going to tell you what the actual problem is. It's not going to be at the very top. So some people get confused about how to interpret these stack traces, and I've actually removed a lot of the lines in the middle just to fit it on this slide. And so this goes over a bit of the code, some of the Python code that I've written to interpret it. And so what are some of the best practices when I'm working with UDFs or trying to verify that I'm working with the right data types? There was another issue that I was working with, was that the input values that I was working with were actually string values. So I had to actually cast the string as a long here into the time delta function. And so sampling your data set to understand different values and making sure that they work within your UDFs are good best Practices, as well as printing out the schema so that you understand what the data types are that are going to be passed into the UDF. And this understanding or interpreting these stack traces are not just for UDFs. It's very common if you're writing RDD code, you're going to see very similar things. So you can apply those techniques to other areas of the platform as well. And then the next piece of it is working through batch updates. As Kyle's mentioned, you can iterate through different dates and times to push out your ETL workflows, and maybe you've run through a batch and you don't know where you've lost track when you've run into an error. So you want to go back and try to identify the records that you've written. Maybe you've done a partial update. You want to fix your code and then rerun this job, but you don't want to handle the duplicates or try to figure out what's already been written. And so one trick that you can use or try to leverage within Spark, there's an input file name function. And what that does is it actually tells you the exact file name for each one of these records. And so if you had an input timestamp that you know you were processing that it failed on, you can go look at the data set, do a filter with the SQL query on that timestamp, and then identify all the file names. You can easily pipe all these file names out and then sideline them or delete them such that you can rerun your batch updates at another time. And so we've talked a lot about ETL best practices, why you should ETL your workflows. It's going to provide a pretty big performance improvement, right? JSON and CSV are all string values, so you have to scan that data set, try to interpret the schemas for them across all your data sets. So it's good for best practices to put them in a binary format where we can prune different columns if you're not, so you don't scan all the data when you're doing processing. And then other best practices on metadata, tips and tricks on how what we typically run into and how do you handle errors within the Spark ecosystem. And some of this is actually handled with structured streaming as we begin to see more and more use cases within structured streaming. So I would say look at that and think about how you can integrate that into your systems if you're thinking about having more real-time ETL systems to bring in the data. Great, and that's it from us. Thank you. We have time for questions.
Hi, regarding the partitioning scheme of the dates, is there any issues with the Hive Metastore continually having newer dates, and essentially the cardinality being infinite on that, vice the year, month, day structure?
Yeah, I think the number of entries that you have will impact the performance because we need to do partition discovery. So there's two ways to actually do it. One is within Spark, if you define a Spark SQL table, we'll do a listing to discover the partitions. Within Hive, you can call add partitions and actually register with the Metastore, but every time you do an update, you actually have to call that metadata operation to add or remove partitions. So sometimes it can be more difficult to manage. Now, you're right that the Metastore, you can't just keep adding all this metadata. You can have a lot of entries, and that can slow down a lot of your job. So depending on how long you want to keep the data around, that might help dictate how many partition directories you have. I would say, personally, I think I've seen a couple thousand directories, unique directories, is kind of maybe a tipping point for some people, depending on the size of your metadata, your Metastore, SQL engine that's holding all that metadata. So maybe not doing it at a day granularity or thinking about doing it on a week granularity. That might be a better option, right?
Does the Spark start with the Spark 2.1 improvements of dynamic partition listing help still?
It does, right?
Yeah, it does. So the metadata in Hive and SQL is is confusing. There's another question, but we can talk about it a little offline, like Hive and,
repeat his question.
So you asked, like, there's been improvements in the way metadata is handled for, in Spark 2.1 for tables. Yeah, so we can talk about this. There's Hive, there's the partition pruning where you pull the individual partition and then you go list the files that are in those partitions you're querying. And so each time you're doing a query, you pull that partition and list the files. Spark, sort of the old way, you'd actually query all your individual files at once and store them in the name node. So if you're only looking at 1 hour worth of partition at a small cluster, that whole listing would take a long time, especially on something like S3, and store it in the driver. So in 2.1, there's been some improvements that you kind of get the best of both worlds, and you can have tables both ways. So I'd look at, there's a great blog post if you want to read more about that, that Eric and a couple people worked on. It's on Databricks' website.
Question.
Hey, you showed us input file name as one of the functions that you can pass in. Are those documented? Do we have a list of those hidden or internal type functions that we have access to?
Yeah, I hide them in my back pocket. That's why you don't know about it. Yeah, these are all actually on the data frames API documentation. So if you go to like a Spark SQL page, it's actually probably one of the top paragraphs. There's links to like Python documentation, Scala documentation, and it's in the, if you see here, the pyspark.sql.functions, there's a functions module that has a lot of really good stuff, right? Instead of writing UDF, if you can use those built-in functions, even if the built-in functions are just chained together, say you want to do a substring and then a regex on it, right? It's better to use those built-ins because they're wrappers into the Spark JVM that's running than to write it within native Python. So that's what I typically do, and I have examples on GitHub and stuff, but yeah, that's publicly available.
Any guidance on how to migrate a Java Spark production pipeline to Scala?
Any tips on, ooh, that's a good one. Tips on migrating a Java program to Scala? I don't know. Brian might be able to answer this one. I think I'm personally very familiar with Python, so that's a good question. I don't know the answer to that one.
We could talk offline.
I called you out, I'm sorry.
It's just not a short answer.
Yeah, it's not a quick one.
Any other questions?
All right.
We got one back here. When doing really large amounts of files, sometimes you get very mysterious error messages. And if you then reduce the number of files, everything runs normal. So are there any hidden settings or tips you could share how to deal with these error messages?
Yeah, so we can talk about the individual error messages. There's been some improvements, like before 1.6, like if you were a Hive table on Spark, like the listing would be done like on a single thread on the driver. So like the listing could take forever. And then the DDL slightly separate between like Hive DDL and Spark SQL DDL. So I recommend doing it with Spark SQL. It'll parallelize the listing as an actual Spark job, so that listing will be faster. And you can actually do this with Spark 2.0 and Hadoop 2 now. Netflix did a pull request because they're very invested in, obviously, Hive to allow that parallelization as well as at least on multiple threads of the driver. So there's different tricks to speed up that listing if you have tons of files. Obviously, if your file blocks are too small, like the first step would be to make them larger. You're going to have to pay it up front in the write, but every subsequent query in the listing is going to be faster. So it's worth that upfront cost for the downstream reads. So those are some tricks. We can maybe talk offline on your individual Spark and Hadoop versions.
Thank you. Great tips. Great presentation. I was wondering for partition pruning whether trying to move away from the Hive Metastore if possible. At least personally, I think if you don't really need it, then might just take advantage of the kind of Spark SQL way of dropping data and reading data and inferring schemas and all of that. However, when there are several processes writing on sort of the same route, is there a way or a trick to prevent reading process from reading partial data in the Spark SQL kind of way without a metastore that actually commits a partition so that following jobs, is there a trick like success file or something that would help us prevent reading partial data?
Follow-up question for him. Where's the Spark running? Are you running on HDFS or S3?
S3, for example.
Oh, for S3, okay. Because that changes the answer. For the HDFS, I believe there's like a temporary directory, and then there's a rename so that it's atomic when you do the write. With S3, move or renames are not like atomic, so I think there is that problem.
Yeah, there's a couple things. Like usually we see batch like it's one production job running, so you definitely sometimes always don't have that process, at least on like the main tables like people are maintaining. But structured streaming is aimed to solve a lot of this, at least where the streams are updating like as the real time. Michael, there's like a file catalog of what's actually been processed, and then it'll atomically commit individual files. So there's a number of things in structured streaming that are going to make this a little bit easier, where you can still get small files coming in, and if someone's running a query, it won't add that file list as committed until it switches that. So there are some things to come, and a lot of these tips and tricks are going to become a lot easier with structured streaming and some of the metadata handling we're implementing in Spark. So we can chat a little bit more too as that moves forward.
And that's all the time we have for questions on the clock, as the AV guys, I'm sure, want to start breaking things down. But feel free to come up. I'm sure both Kyle and Miklos should be happy to talk to you privately. And that's a wrap. Thank you very much.